Session 5.2, Finding Theoretical Probabilities. Remember, we say theoretical probabilities is talking about the calculation. We do have the specific formula to calculate the theoretical probabilities. And also, we will learn find the probability of the complement of an event and how to use the basic probability rules. So first, let's talk about what is probabilities. Probabilities is always between 0 and 1, okay? So you're gonna see I write it in the simple. This is a probability of the event X is always in between 0 and 1. So for these chapters, when you calculate the probabilities, if you could find your probabilities less than 0 or greater than 1, that means you make a mistake. Can be expressed as a fractions, decimal, or percent. Okay, I usually use the decimals. An event has a probability of 0 only if it can never happen. So when I flip the 6-side die here, I only have a 1, 2, 3, 4, 5, 6 side of the die here. What is the probability to get the 7? Is it possible? I want to get the probability of 7. So no matter how many times you roll the die, you won't be able to get the 7 because there's no 7 there, right? It's only from 1 to the 6. So I would say the probability of getting 7 will be equal to 0 because it never happened. And an event has a probability of 1 only if it is certain to happen. So when I flip the coin, I would say, what is the probability to get head or tail? Okay, I can get or the tail. When I flip the coin, it's only get head or tail. So the probability to getting head or tail will be equal to 1 because it will happen for sure. Okay, the notation. P will stand for the probability. And then we always name the events A, events B, or events C. So you will write like something like this. Probability of the events A occurring. Okay, I need to see this notation on the exam. For example, toss a coin. When A represents the event, the coin lands on heads. So we'll be putting probability of event A means probability of the coin lands on head will be equal to 1/2 or 50% or 0.5. The complement of an event A to the Z power. Okay, I want you guys to highlight this part here. The complement refers to the event not occurring. The complement of the event A is written. You could use the A bar here, or you could write the little c on the right hand corner. Okay, some book using this notation for the complement. Some book using the A for the to the C power has the notation of your complement. So what does the complement means? You could think about the event happen and not happen. For example, when I toss a coin, I will let the event A equal to coin lands on head. So what is the complement of A? Will be the coin does not land on heads. The coin does not land on heads means I will get the tail. So complement means the event occur or not occurring. Another example, wait for a bus and note its arrival time. And then we let the event A, the bus arrives on time. So what is the complement of A means? The bus does not arrive on time. Okay, when you guys see finding the probability, finding something not, does not, will not, you could think about the complement. Okay, formula for the complement. Probability of A does not occur will be equal to 1 minus probability of A does occur. So this is like I write it in notation. Okay, P of event A complement equal to 1 minus probability of the event A. So for example, when I say there is 30% chance it will rain tomorrow. So what is the complement of this event? So think about it. Event A will be it will rain. So the complement of A will be it will not rain tomorrow. So if there is 30% chance it will rain, so tomorrow it will 70% chance it will not rain. So 30% plus 70%, that will be equal to 100%. So that's why they do have this formula. When you happen and will not happen, when you add it up, that's equal to 1. Or another way to write is going to be 1 subtract A does occur will be equal to A does not occur. So look at this example. Let event A represent the event the candidate wins an election. Suppose probability of A is equal to 0.70. Find the candidate does not win the election. So highlight those words, does not. So you're going to think about the complement. So we're going to use this formula, right? We're going to let event A of the complement, the candidate does not win the election. So plug it in, 1 minus 0.70. So you're going to get 30, right? 30% of the chance the candidate does not win the election. Okay, for the probability, we do have a lot of different formula. So I need you guys, when you read the questions, highlight some key points. Like these questions, you could see the does not. Okay, highlight that. When you have a not, you're going to think about the complement and the complement formula. Okay, sample space and the events for equally likely outcomes. What does the event means? Any collection of the outcomes in the sample space. For example, the event, obtain an even number in one row of 6-sided die. So first, let's talk about what is the sample space. Sample space means all the possible equally likely outcomes for the experiment. When we roll the 6-sided die, what is the sample space? What possibly you can get when you roll the 6-sided die? You should be getting 1, 2, 3, 4, 5, 6, right? We do have a 6 number on the die here. Okay, so we call this is gonna be the sample space. And then the outcomes. This is what we want to get. We want to get the even number. So we have a 2, 4, 6 in here. This is gonna be my outcomes. I need you guys to know how to write down the sample space and also the outcomes for each of the questions. Then you will be able to find out what is the probability. Okay, for example, roll a fair die 1 time. Fair die means they will have a equally opportunity to get on each number. So again, this is the sample space. And then the event, roll an odd number. Okay, which one is gonna be your odd number? We have a 1, 3, and 5, right? So this is gonna be my outcomes. Okay, one more time. Roll a number less than 4. Okay, so this is the event. What is the outcome here? Less than 4. So the outcome is gonna be 1, 2, 3 here. Okay, using a sample space to find a theoretical probability for equally likely events. Equally likely events is really important for the probability. That means they do have a same chance to getting the outcome. For equally likely events, so this is going to be your formula. Probability of the event A will be equal to number of the outcomes in A and then the number of all possible outcomes. So this is talking about on the top, the numerator here. This is talking about the outcomes. On the denominator, this is talking about the sample space. For example, roll a die, let A represent the event, get a number less than 3. Find the probability of A. We do have the sample space from 1 to 6. And here we do have 1, 2, 3, 4, 5, 6. 6 outcomes here. And then the outcome of the event A less than 3. So we only have a 1 and 2. In here, we only have a 2 outcomes. So we're going to plug in on this formula. Probability of the event A will be the outcome of A over the sample space. Simplify it. So you could give me the fraction as the final answer, or you could round it to the decimal space. Okay, using a sample space to find a theoretical probability. Example, a family has 2 children. Find the probability that both children are girls. So first, we're gonna let the event A, okay? I would say event A represent both are girls. So this is what we're looking for. And then I need you guys write down the sample space. So when you have 2 kids, what is the sample space? Either you can have a boy and a boy, right? Or you can get a boy first and then a girl. Or you can get a girl first and then a boy. Okay, keep in mind that the order doesn't matter. To get the boy first or get girl first is going to be the different order. Or you can get 2 girls. So write it down, the sample space. And then what is the outcome? Outcome of the event A, both are girls. Okay, so this is going to be my event A outcome. So find the probability. So we're going to count. I have 1, 2, 3, 4. Okay, 4 possible outcome. And then the event A will be 1. So probability of A will be equal to 1 over 4. Okay, try to do these 2 questions. Okay, let's do together. Example 6. 30 people were asked about the colors they like, and here are the results. Red 10, blue 15, and green 5. If a person is selected at random, what is the probability that this person likes the red color? So first step, write down the event. What is your event A? This person's like the red color. Okay? And then finding the probability of A. So we do have 10 people like the red color. And then the total possible outcome will be 10 plus 15 plus 5, which is going to be 30. So it's going to be 1/3. Okay, 1/3 of the people likes the red color. Example 7. If 2 dice are rolled, what is the sample space? So this part A, we are not calculating the probability. We only want to find out the sample space. Similar to the question on number 5 here. First, I want you guys to write down the sample space. Think about what is the combination when you roll the dice twice. Okay, so we do have a 1, 2, 3, 5, 6 for one die. Another one is going to be 1, 2, 3, 5, 6 for another die. So what is the combination? How many sample space do you have? Think about it. So when you roll 2 dice, you can get the first one, you can get 1, second one can get 1. So the combination is going to be 1 and 1. Or you can get 1 and 2, or 1 and 3, 1 and 4, 1 and 5, and 1 and 6, like that, right? Or another combination is I will get 2 here and get 2, 1, 2, 2, 2, 3, 2, 4, and 2, 5, and so on. So think about it. How many sample space do we have? Okay, check your work. We do have 6 times 6. We do have a 36 sample space in here. And then one more time, 1, 2, and 2, 1. This is a 2 different sample space. But 2, 2, 3, 3, 4, 4, we only have a 1, okay? So we do have 36 sample space. What is the probability if the sum of two numbers is equal to 4 and let event E has the set of possible outcomes? So which sample space, when you add it up, is going to be equal to 4? We have 3 plus 1, 2 plus 2, and then 1 plus 3 here. Okay? So finding the probability of E here, we do have a 3 outcomes out of 36. So it's going to be 1 over 12. Okay. Combining events with N. An event belonging to A and B must belong to both A and B. So when we're talking about the probability with N, okay, N means both of them must be occur at the same time. For example, if event A represent wearing a hat and the event B represent raising a hand, then someone in A and B is wearing a hat and raising a hand. So N, it must be occurred at the same time. Okay, so I have this girl, Maria, wearing a hat and raising a hand. And David also. Okay, so this is going to be 2 outcome out of 1, 2, 3, 4, 5, 6. Okay, so that will be, I want you guys to remember this notation. Okay, this is a probability of event A and event B occurs. Highlight this one, you will see this notation a lot, and I want you guys to know how to use it also. So that would be 2 out of 6, which is going to be 1/3. Okay, next example. If the event A represent wearing a hat and event B represent raising a hand, then someone in A or B is wearing a hat or raising a hand or both. So this is the combining events with and, okay, and it must occur at the same time. Another combining events is called or. So or means I can get A or I can get the B, okay, or both, okay, I can get both of them. So if event A represent wearing a hat and event B represent raising a hand, then someone in A or B is wearing a hat or raising a hand or both. So think about it. I have one girl wearing a hat and wearing a hat and wearing a hat. Or it can be raising a hand, raising a hand. But you're gonna count number of the people. So 1, 2, 3 here. Okay? So this is the notation of or, the union or. So that will be 3 over 6 in here. And the answer is gonna be 1/2. Okay, finding the probabilities from two-way table. In the 2012 General Social Survey, people were asked about their happiness and were also asked whether they agree with the following statement. In a marriage, the husband should work and the wife should take care of the home. The following table summarizes data collected 1 to the 3 decimal space. So you could see this table. We do have a happy and the number of the total, unhappy, number of the total, and agree, number of the total, don't note, and disagree. And this is, remember, we call this is going to be the grand total. So suppose a person is randomly selected from this group. Find the probability that happy and agree. Remember and it has to be happen at the same time. So find it out how many of them is going to be happy and agree. Happy and agree. Okay, so that will be 242. So, and before that, we're gonna let the event A become the happy, event B will be agree. So when we wind the notation, probability A and B will be equal to 242 over the grand total. Total will be 1146. Okay, use your calculator. 1 to 3 decimal space. Okay, you should got 0.211. Okay, B. Probability of happy or agree. I can get happy or agree. So think about it. How many of them are happy total? Will be 991. Okay, happy or agree. Okay, you don't add up these two numbers. Do you guys know why? If I circle it here, circle it here. If I add up 287 plus 991, I will be duplicate this number. Okay, we only pick this number 1. So either you could do 242 plus 65 plus 684 and then plus 45. Or you could just use 991, which is this part of the total happier, and you only add up the 45 here. Okay? So A or B over the grand total. Use the calculator. You should get 0.904. Okay? Hey, put the star for these questions. Okay? This is an or. You could take either one of it. But just be careful when I add up the numbers. Don't duplicate this one. Okay? This is belong to happy and agree. Okay, C. Probability of agree or don't know. Same idea. Agree or don't know. So think about it. Before that, I will add let the event C be the don't know, okay? So it will be easier for me to write the notation. So B or C, B will be the agree. So how many of them are agree? 287. How many of them are don't know? 95. So 287 plus 95 over the grand total. You should get 0.333. Okay, mutually exclusive event. Two events are said to be mutually exclusive, or you could say disjoint if it is impossible for both events to occur. For example, when a coin is tossed, it is impossible to get both a head and a tail. Right? When you flip the coin, either you get head or tail, but you can't get both of them. So we call this is a mutually exclusive event. Okay? And the picture is going to be looks like that. So you could see we do have a probability of heads here. This is a probability of tails in here. Then they say this is a disjoint, and this is the diagram to represent mutually exclusive. Addition rule for mutually exclusive. So if I want to find the probability for this picture, will be probability A or B equal to probability A plus probability of B. So that would be similar to example for this part C here. Okay, you just need to add it up probability of B plus probability of C. So on the event C, agree or don't know, they are mutually exclusive. Okay, they can't happen at the same time. Mutually exclusive. Not mutually exclusive. Both events can occur at the same times. For example, it is possible that I'm eating my breakfast while I'm reading a book. I can do it at the same time, right? I can do just eating my breakfast, or I can just reading a book, or I can do it at the same time. So this is called not mutually exclusive event. So the diagram is going to be looks like that. So you could see at this part, this is maybe the probability of eating my breakfast. And this part, the red here, probability of reading the book. And in the middle, this part here, this is talking about A and B. So in the middle here, this is represent the probability that I'm eating my breakfast while I'm reading a book. Okay? So we do have the addition rule for not mutually exclusive. You could see the intersection in here, right? So we're gonna do probability A or B equal to probability of A. We're gonna calculate this probability plus probability of B, okay? You could see when I circle it, I duplicate of this part already. So that's why I need to minus probability A or B. So when you guys working on the probability questions, if they ask for or, you have to first think about it. Are they mutually exclusive or not mutually exclusive? Once you know, you would just apply the formula directly. Okay? Okay, try this previous example. We're gonna do it one more time, but this time I need you guys to think about it. Is the event are mutually exclusive or not mutually exclusive? And also, I want you guys apply the additional rule. Okay, let's do it together. Suppose a person is randomly selected from this group, fine. We're gonna let A be that happy, B is agree, and C is gonna be don't know. Find the probability that happy or agree. I would recommend you guys circle it if you have the table here. So this is my happy, and this is gonna be agree. So remember the diagram from the previous slide? They do have the intersection. Okay, look at the picture here. They have the intersections. When they have the intersection, that means the event is not mutually exclusive. So you want to apply this formula. Okay, you could see the intersection here. So not mutually exclusive, so we're gonna using this formula. Okay, probability of A will be the happy, so it's gonna be 991, and the probability of B will be here 287 minus A or B minus the intersection, that will be this part. Okay, A 991, the B 287. Take it out the intersection 242. You're gonna find 0.904. Okay, C. Find the probability that agree or don't know. So circle the agree. Don't know, it's gonna be here. Okay, did you guys see they have the intersection? No, right? No intersection. No intersection is gonna be here. So that will be mutually exclusive. And this is gonna be the formula. Okay? So straightforward, mutually exclusive, we're gonna apply this formula. Agree, probability of agree will be 287 plus probability of don't know will be 95. You should get 0.333. Okay, and one more time, mutually exclusive event or not mutually exclusive event, for sure that will be on your midterm. Okay, you're gonna see a lot of the questions is gonna be using this formula. Okay, I want you guys try to do the example 10. That's A, B, C, 3 parts. Make sure you guys let the event, okay? Let the event A, let the event B, and let the event C. And also, one more thing. On the exam, I need to see that. I need to see you guys write down the event and then using the notation. Okay, tell me, are you looking for the probability of event A or event B or A or B or A and B? Okay, on the midterm, one more time, okay? If you only show me the final answer, you only get 1 point. I need you guys show your work, get the final answer, and 1 to the decimal space that I mentioned in the questions. Okay, and also I need to see this, okay? Example 10. This table shows marital status and educational level for a random sample, 1 to 3 decimal space. So you're gonna see the table here. That's a two-way table, and then you do have a grand total in here. What is the probability that the person is married? Okay, this is the basic probability, right? First, let the event A be married, and then write it down. Probability of A equal to how many of them are married? 408. Okay, so 408 over the grand total 665. Use your calculator, 1 to 3 decimal space. Okay, B. What is the probability that the person is married and has a college education or higher? Married and college or education is higher. Like here, right? So let B has a college education or higher. And then we're looking for the probability of A and B. Okay, A is married already. So A and B equal to 98 over 665. You should get 0.147. Okay, C. What is probability that the person is married or has a college education or higher? So or, when you see the or, that's the two events. You need to think about it, is the events are mutually exclusive or not mutually exclusive? So it will be easier when you guys have the table. So I will just circle it. Married. Circle the married. Has a college education or higher. So I'm gonna circle this one. So do they have an intersection? Yes, right? They have the intersection. So will it be mutually exclusive or not mutually exclusive? That will be not mutually exclusive because they do have a intersection. So write down the formula. Okay, plug in one by one. So probability of A will be the married. So 408 over 665. Probability of B, that's a college or higher, will be 143. Minus the intersections, that will be the 98 in here. Okay, so you should got 0.681 here. One more time, when you guys see the or, think about mutually exclusive or not mutually exclusive. Okay, last example. Probabilities with OR. Roll a fair six-sided die. Find probability of rolling an odd number or a number greater than 3. Okay, so for this one first, let the event A and B. A will be the odd number, B will be a number greater than 3. So again, think about it, or. When you see or, write it down, this event will be mutually exclusive or not mutually exclusive. It's better you guys can write down the sample space. Okay, sample space will gonna be from 1 to 6, right? A six-sided die here. So I want the A odd number. Odd number will be 1, 3, 5. B will be a number greater than 3. Okay, so which number is going to be greater than 3? That will be 4, 5, 6. Okay, do they have an intersection? Yes, right? You could see the 5 will be the intersection. So this is not mutually exclusive. And this is going to be the formula. Not mutually exclusive. So you're going to do it one by one. First, what is the probability of A? To get the odd number, you do have 1, 2, 3. 3 over 6. Probability of B, a number greater than 3. So 1, 2, 3. 3 out of 6. And then what is the intersection? I only have a one number is intersection, so it's going to be minus 1 over 6. So that will be 5 over 6 in here. Okay, last one. Rolling a fair six-sided die here. Finding probability rolling a number less than 3 or rolling a 6. So same idea, let the event C and the D here. This is the sample space. So think about it. If the event is mutually exclusive or not mutually exclusive. Okay, a number less than 3. So this 2. D, rolling is 6. So this one here. So do they have an intersection? No, right? So that will be mutually exclusive. So the formula. Probability of C will be 2 over 6. This is going to be 1 over 6. So it's going to be 1/2. Okay? So these sessions, we talk about the basic probability and the complement. Remember the complement formula? When you guys see the not, will not, does not, think about the complement formula. And then we also learn the and or. Okay, for the or, we have a mutually exclusive event and not mutually exclusive event. Okay, one more time on the exam, I need to see you guys write down the event and then write down the probability of that event equal to, so your word and the final answer. That's it.